All right, so I'm going to talk a little bit about what it takes to run your own LLM inference and support like applications of LLMs, doing it yourself with.
Hi, sorry to interrupt. Can you use the mic for the recording, please?
Ooh, we're getting a recording.
Thank you.
That's fancy. Okay, wonderful. Yeah. Also, the voice of God. I don't know. That's big. I'll have to be on my best behavior on this talk. I'm being watched. Great. So once more for the recording, I will be talking about what it takes to set up your own LLM inference service and support LLM applications using pre-trained foundation models. So the first thing to do is sort of answer the question of like, why? There are many things that you can do yourself, but not all of them are good ideas. So why do people want to run their own LLM inference? One important caveat here is that if you need the latest and greatest frontier capabilities, open models are not the place to go right now. As with like many types of software, the edge is in the proprietary systems. And it's sort of the more generic, sort of commoditized capabilities like summarization or tagging or like structured output extraction. Those are the things that open models can do well. Loose heuristic is like, if this seemed like a good idea playing around with the initial launch of ChatGPT, it might actually be a good idea with open source models now. So that is like kind of an initial kind of like go, no go, basically. Then after that are questions like, what makes this a good idea just because it's possible with those open LLMs? Number one is that you can often sort of like save money on your LLM inference by kind of picking the specific tasks that you're working on, whether, summarization or support chatbot or whatever, and making like a smaller fine-tuned or distilled model based off of these open models. So then you can run it, it's cheaper and it's like narrower, it's not as good at everything, but it's good at the things you need it for. That it's challenging though to save money running LLM inference. You might think, oh, these people are like a monopoly, they're the only ones like running these big models, like I can totally run my stuff cheaper. The answer is that actually there's quite a bit of competition for running LLM inference, both for proprietary models and as providers of services, like running open models that you could run yourself for you. So there's quite a bit of competition. So it's not like cloud services where like, oh, there's a 10x markup and like I should just run this myself. So you have to be pretty good and identify something like being able to fine tune before you can like really save money on like a token by token basis. One way where you can do a little bit better is there are generally like rate limits on a lot of providers. And sometimes you're just like, you know what I want to do? I want to do this backfill where I want to like summarize every single support ticket since the company started. And that's like 10 billion tokens. And then you need to just do that. And that you need to run that for like an hour and then you don't need it anymore. And that you will frequently run into rate limits that people are like, oh, well, if you want to get more than 1 million tokens a minute, then you need to like sign up for XYZ. So especially if you can use like a serverless platform, then you can just like get a hold of the resources you need for a quick like backfill or for a like cron job one-off like irregular work. And then that like, saves money also on like, buying your own servers. But then probably like the biggest thing like active right now is that people want to like manage the security and the data governance more tightly. They don't necessarily trust either like a proprietary model provider or somebody like running open models. They don't necessarily trust them with their data despite like promises not to train on it. Some of that is a little bit like paranoia. It's like very much not in the interest of those people to like do scuzzy things with data. But if it's more of a security, like, oh, we're a bank, our security model is like basically air gapped, then you have no choice. The last one is gaining additional control over inference and its applications. So this is like the classic reason why people want why they want open tools is that they want that like hackability. They want like and control. They want to like extend it and do something slightly different. And so right now, I would say with language models, there aren't a ton of like killer workloads yet where this hackability is super powerful. I think if people have seen like Golden Gate Claude and the sparse autoencoder work, where you can kind of like use a little bit of ML on the internals of the model to like pull out behaviors and sort of control them like with numbers, like programmatically. That's a powerful technique. There are lots of things you can do if you have access to like probabilities output by the model and not just the tokens, which not every provider gives you. So there's like little things already starting to show up, but there's not a ton yet. I think for all of these, the long-term balance is in the direction of these becoming like kind of more important over time. Like it'll become cheaper to run these things yourself. The software for running it will get better. The like complex workflows that make use of models will like become standardized or become more obvious and readily available. They'll be discovered by researchers. And so I think the direction of things is towards this. I'd say right now it's only just it's like very case by case whether it makes sense to do it yourself with open models. Okay, so with that aside, let's just assume that this is a good idea and plow forward. So there's a bunch of steps required to get to the point where you have something that's as good as these available services. You're going to need hardware to run it on. You're going to need evaluation to determine whether you're running the models properly and whether they are like good. You're going to need to then like sort of pick models and select models on that basis. Then you can do a lot of that just with regular PyTorch and transformers, but when it's time to serve inference, like you're going to need a specialized inference serving engine or framework. And then like that needs to then be integrated into applications. Like other software that you are running needs to talk to this. And what does that look like? And then this whole setup needs like monitoring and observability so that you can improve it over time. So this is the whole set of things to get to the point where you're like, you have your own LLM inference service and it is like both like delivering on its SLAs and SLOs, and then it is also like a place where like value is accumulating, where the like work that you are doing is creating like a differentiating like edge for your company for delivering these features. So let's go into all of these. So first, on the hardware side, for now, the answer is TLDR, just use NVIDIA GPUs. Diving like a little bit deeper into that, like why GPUs, why do we need accelerators for this? The basic answer is that there's a very big difference in how like silicon is allocated. Like the area on a chip is like very precious real estate, not dissimilar to the city we're currently in. And so the choices about where, like what that is used for are very revealing, and they are like and they reveal the like constraints of the system and the goals of the system. So with a CPU, a very large fraction of the die, as represented in this diagram, is on caches and control flow. So it's the gold, purple, and blue parts. And then only a smaller fraction of the die is on actual compute. And then there's like a small number of big compute units. The GPU is very different. There's very, very little spent on like local L1 caches and very, very little spent on control flow. And everything else is like a bunch of tiny compute cores. And so what this system is set up to do is to do the same operation, so simple control flow, and just do it like a lot at the same time. And then secondarily, it's also set up for very, very fast communication between the memory, the orange at the bottom, and those compute units. And that is exactly what that's like kind of what you need in graphics. You need to move like textures and vertices around, and then you need to transform all of them in the same way or with slightly different parameters. And with neural networks, it's very similar. We need to like move the weights in, and then we need to do these like very simple collections of like multiply and add, multiply and add, multiply and add, and you just do them at like the billions or trillions of operations per second scale. And so that's like GPUs are designed for this. and it's like extremely difficult for CPUs to like match them at this. This is like the perfect workload for them. This is also a reason why, by the way, it's like pretty hard for any alternative to GPUs to like beat GPUs at this game, because the networks and the GPUs kind of co-evolved. There's some caveats and nuance to that. If you're interested in like alternative hardware, catch me afterwards. I dropped the slide on that. So for now, the like game in town for building GPUs is NVIDIA. You want GPUs that are focused on inference, not on training. So like training neural networks is very different from running them in production. There's like a number of differences in the workload. Most notably, there's a lot more network communication in training. And because so there's all this stuff around the GPU, like liquid cooled network interface cards and all this stuff to deliver like high throughput during training. When you're running the model, you don't need that. You're just like sending a couple of tokens in and getting some tokens out. You aren't passing around gigabytes of data every couple of seconds. And so you want GPUs oriented to that. The interesting thing is that the inference problem, because it doesn't involve this other complicated shit like InfiniBand, it's actually like an easier thing for other people to build. So AMD GPUs are like still catching up to NVIDIA on performance per dollar, but they're catching up like faster for inference workloads than for training workloads. So like this advice may change. It's like worth paying attention to. Eventually, this is likely to be true for like non-GPU chips as well. Again, because the like workload for inference is so different from training. But that's not true yet. Even no matter what like Cerebras or Grok says in their press releases, it's not true yet. So what you want in general when building like an LLM inference service now is you want something that's like a recent but not totally bleeding edge GPU. So like the Blackwell GPUs are like, if you got a really close connection with one of the hyperscalers or with NVIDIA, maybe you can get a hold of those, but you're going to find they're like hard to use and none of the software supports them and like yada, yada, yada. Whereas the generation before, now a lot of the hyperscalers and big labs are kind of like selling their hand-me-down H100s. And so they're getting cheaper. And then also there's like fairly mature software for using it. And then the generation back, the Ampere generation, like very solid, dependable, like lots of deployments, lots of availability. So like if you can run your workload on that with acceptable parameters, it's a great choice. So the particular GPUs in each generation, with the Ampere generation, it's like probably these like A10 and A40 GPUs. With the Lovelace generation, which is kind of like baby Hopper GPUs, that like the L4 and the L40S in particular are kind of the ones people like. Hopper and Lovelace are kind of the same generation. H100 is a bit more training oriented, but if you can find them like on the cheap without all the fancy training infrastructure around them, then actually they make not a bad choice, and they will have better performance than the Lovelace. Especially if you're thinking about buying GPUs, the like primary constraining resource is the size of the off-chip RAM or the DRAM here in this diagram. And just because like if you can't fit everything in there, then you need to spill the disk. And it's like not dissimilar to when like virtual memory spills to disk. It's like technically the thing still runs, but now it's like glacially slow. And it almost would be better if it crashed. Like that's kind of, so if you can't fit it in the VRAM. So that's the thing you want to make sure you have enough of. And then like you'll find then compute and memory bandwidth, like how fast can you move through numbers and how fast can you get things out of memory and into the compute units are like kind of close behind as the like constraints. I'll talk more about this in a second, but all of these resources are freed up by quantization. If you can like just shrink the size of the floating point numbers that you're working on down from 64, 32, 16, 8, 4, maybe 1 bit, then you free up capacity, you free up bandwidth, you can do more compute instructions on fewer bits. So that's like a very critical part of this. I'll talk a little bit more about quantization in a couple of slides. Before I go on, maybe pause for a question or two about this, about hardware. Yeah.
How are you benchmarking like how lossy the floating point gradations are? Like, what are you using?
Yeah. So the question was like, how do you measure how lossy these quantizations are? So yeah, so this quantization is like definitely lossy compression. The usual thing that people do is they run the model on benchmarks and they look at like benchmark numbers and they look good. The answer to this is like you kind of have to benchmark it on your own task. Like I don't really trust these generic benchmarks to tell me whether it's going to work on my particular task. Luckily there's like pretty good libraries for doing the compression and evaluation. So that's kind of what you got to do. The answer, I think the high level thing is that it is surprising how low you can go. Like you can actually do 4-bit computations and like with some tips and tricks, you can get it to like be pretty good. The takeaway, so I studied training neural networks in grad school, and kind of my view on this is that really this thing is like, it's more of like an analog computer that we like simulated on a digital computer due to skill issues. And so like you don't actually need, unlike like integers that are used as like pointers, every single one of those bits has a meaning. Every single one needs to be exactly where it is. You know, that's like the sort of like clockwork like genealogy of computers. But the like, you know, the numerical integrators that were the competitors to digital computers back in the day, that's more like what a neural network is like. And you can slap a numerical integrator on the side while it's running and you'll only get slightly wrong, you know? So I think that's like where this like why we can do it. But yeah, would love to talk more about that. There's been some cool recent research results as well. Yeah, quick shameless plug for Modal. So we're an infrastructure startup. We make getting a hold of GPUs like the ones I was just talking about really easy, along with just like all kinds of distributed system stuff. This is some real benchmarking code that our co-founder posted in Slack. He was like, oh, by the way, I'm gonna try and like scale up 100,000 inputs to H100s and see like how, like if it takes the system down. And the answer was no. We like topped out at like a couple hundred H100s, all doing time.sleep and printing. So if you want to make it, you know, as easy as possible, as easy as this, to get a hold of the hardware infrastructure you need for running LLMs or other things, check us out. All right. So we got the hardware. Now what do we do? The first step is actually determining how you're going to evaluate your like success criteria for your inference and like for running these models. This actually kind of like comes before anything else. In some ways, it's sort of like test-driven development. It's like you write the tests, then you write the software because the tests help you know whether the software is right. Also, like test-driven development, it's the sort of thing that people say to do it in that order in a talk, but then they go home and they don't actually do it and nobody actually does it. But it is the right way to do it, and you should aspire to doing something like it. But the real reason to want to do this is that you may have heard the aphorism "data outlives code," attributed to Martin Klutman. That says like, oh yeah, you have data that's years old in your database, but your code is like probably months old, or and similarly, models kind of like come and go. Like you probably couldn't pay me to take delivery of the GPT-3 weights right now. 170 billion parameters, and the thing is like worse than like, you know, like a 3 billion parameter fine tune that like some anime profile picture uploaded to Hugging Face. Like I don't need that. The models, like they decay very quickly. Like what allows you to like say, okay, that model is not enough anymore, I want this other model, is evaluations, is your ability to say like, this is better, this is worse. Like going back also to the question about quantization, like how do you know whether you've quantized too much? Well, you got to run the thing and check. So, and I say you like evals are not just like these, there are these big benchmarks and those are helpful for like vibe checks and sort of order of magnitudes. It's kind of like if you've worked on databases, there's like the Transaction Processing Council has this like benchmark for databases. And fun fact, certain database vendors that may or may not be associated with private islands have been known to do things like add secret little extra bits to their query optimizers that detect whether they're running inside the benchmark and like turn on optimizations that are just for that benchmark. Similarly, model providers, whose names will not be mentioned, may be training on some of these benchmarks or watching the benchmark numbers while they train. And so making decisions that make them look good on those benchmarks, but don't like correlate as well with their downstream utility. So as with the benchmarking in databases, it's one of these like trust but verify type situations. So what you really want to do is build your own like methods of evaluation. Like part of it is like trust no one. Another part of it is like your application, your domain, even as broad a domain as like healthcare, programming, like internal tools for a startup. Like those are narrow enough that there's actually probably quite a bit of lift over these like generic evaluations about like hallucinations and like sentiment and tone. So like the way to do this is to spend time with data, like data that is coming into your production systems that is related to what you're going to deploy on LLMs, like time with domain experts, like kind of like collecting up these like internal expert judgments about whether things are good or bad. So like annotating, collecting up this data. The tools for doing this don't have to be super complicated. Like I've seen people do this very effectively with like a spreadsheet, a Jupyter notebook, anything where you can basically like collect up information, like track it over time, go back to it months later, make a chart, calculate an average. Like that's all you need. Like there's fancier stuff. There's embeddings and like there's LLMs as judge and there's like frameworks, Langsmith, weights, biases, weave, brain trust. But like you kind of have to like buy into those things. And if you don't really know what your evals are going to look like you don't know which of those you're going to want. And also frankly, a lot of those framework providers like don't know what you want either. And they're kind of figuring it out as well. They're like looking for design partners, unicorn hunting. And so like, it's not like, you know, partnering with somebody to bring an observability stack to your traditional software where like they've got like experts who've been doing distributed systems observability for 10 years who will like help you not foot gun. Like, yeah. So start simple and use just basic tooling to set this up. Yeah, the like primary thing that drives this is like spending time actually looking at data, like reviewing it closely. This is basically every instructor and guest lecturer in Jason Liu's RAG improvement course talking about saying the phrase, look at your data or look at the data. Yeah, it's the like primary way that you like construct these evaluations. Okay, so once you have like some baselines, like 10 prompts that you want to check or behaviors you want to emulate, you now are like equipped to go out and kind of like pick models that you might want to like run and serve. So yeah, this is all very fun and exciting. There's new models every day and cool new techniques. Like don't start this until you have evals. Don't start until you have a way, like even just like 10 inputs in a Google Doc. The model options right now are like fairly limited in that for the level of capabilities that's actually legitimately useful and like in a format that's like cost effective to run, very few options. Meta's Llama model series is like very well regarded as the strong backing of Meta. And there's like a growing community kind of building on it. It's really important to open source success is like kind of getting community buy-in, and Llama seems to be kind of succeeding here. There's like merge kits and merges on top of it. There's fine tunes from people like Noose Research. There's folks like Neural Magic doing like special quantizations and like putting them out there and building them for Llama, like compatible with other things, but Llama first. And that's all stuff that's going to make your life easier and allow you to ship faster. The kind of runner-up right now in my mind is the Quen series from Alibaba, like very solid. There's slightly more restrictive licenses than Meta, like the smallest and largest Quen models are under like a non-commercial license, so there's like a little bit of concern there. There's a bunch of models that are out there that are under like very bad licenses or non-commercial licenses. So that kind of cuts them out of consideration here. So they're like, these are kind of like if you want to launch like next week, like those are kind of your two options. There are some others that are like also pretty good. Keep in mind, like, maybe follow them on Twitter or whatever, or on Hugging Face. You got the like Microsoft Phi model, the Allen Institute's Olmo model, and Molmo multimodal model. And you've got Mistral and their like Mistral, Mixtral, Pixtral series. So they're all like pretty good, and they like are doing like they're like kind of keeping up, maybe a little bit behind. It does take a really long time for people to get good at making models. So frequently they'll like put out an initial model and it's like not that impressive. And in fact, before the Llama series, there was the OPT, the Open Pre-trained Transformer replication of GPT-3 by Meta. And that was not a very good model. And but they clearly learned a lot from that process. So similarly, like Snowflake Arctic, Databricks DVRX, like they were like cool for like a day, and then like, oh, there's like better models already. Like, but like keep your eye out to see if they like, and hopefully that means we'll get like lots of options with different, different affordances and capabilities. Yeah, with models, like kind of correlated with models is like this like quantization, like shrinking the size of floating point numbers down. It's like very important for getting good performance out of these things. They're frequently, I guess I had this slide here because back in the day, you kind of had to like do this yourself a lot. Like you had to have your own calibration data and you had to have like kind of a lot of it. And it was kind of like an extra step of training. But actually, now that I think about it, I should probably move this slide up to the hardware section, because really now this is something that's like fairly plug and play for like for quantization to 16-bit, 8 and 8-bit. And so you can kind of just like do this very quickly. It's like more of a compile step, like more like traditional software and less like an ML project. So it's less like making a new model. So yeah. There's kind of like multiple things you could quantize. The ideal thing is quantizing the weights, and then also like the weights are quantized, and then when you calculate stuff with the weights, the output numbers are then also in that low precision format. That's like native low precision throughout the whole model. That's ideal. It's not really there yet right now. Like Flash Attention 3 and the latest PyTorch kind of have support for this in their attention kernels, but kind of actually don't and don't get the full performance benefits. Likely to change in a couple of months, but that is where you would like really get a ton of benefit, because you would like double all your like compute bound workloads would double in speed. But at the very least, the like weight quantization like makes it easier to fit models. Like you can get a 4-bit machete kernel version of Llama 3 405B that does well on benchmarks and fits in 200 gigabytes or 220 gigabytes of VRAM. So that means you can run it on like 4 H100s instead of 8. And that's a pretty big win. Yeah. I think we kind of already talked about the benchmarks, but the quality doesn't seem to be harmed, especially on like short, like multiple choice benchmarks, short responses. But you're like likely that the errors will accumulate over time. So the longer the model is like running for, and like longer conversations, longer contexts, you're like more likely to see degradation. I don't know if there's like formal research results on that, but that's kind of the intuition. So you definitely want to evaluate this in order to decide whether this is a good idea, whether this is tolerable for your task. Last, I think, like when you're developing applications on top of your LLM inference service, like the temptation is to immediately jump into fine tuning, especially for people who are like classically ML trained. But it's like a whole bunch of additional extra lift. It's like, it's going to up the resource requirements of everything. You're going to be going multi-node, like almost like guaranteed. And so you want to like get as far as you can with prompting models before trying out fine tuning. Prove out the POC in like JavaScript or Python before you like devote months of engineer time to writing it in Rust, like same idea here. Okay. So we we've got our hardware. We've built some evals that are allowing us to confidently pick between models. We're doing all of this probably in like PyTorch or transformers. Now it's time to like scale this thing up, and those are probably not going to cut it. You're going to need an inference framework. This following section is an unpaid advertisement for the vLLM inference server project. So the reason why you can't really, you want to kind of like stick with the like PyTorch CUDA combo. Like that's actually a pretty good stack. A lot of people are like, Python, that's slow, I should rip that out. It's like, no, Python is sort of just like driving the GPU, like, and you as the driver of a car do not need to be able to go at 100 miles an hour. You just need to be able to like push your foot down and turn the wheel. And that's all Python really needs to do for like running GPU accelerated workloads. So like that's actually pretty good, and PyTorch is pretty good at it. There's like some performance things that like torch.compile is pretty good at, is already pretty good at fixing. But the real problem is that there's a bunch of things on top of this that you need to build to like make inference fast. In this, like to run an inference server, there's all kinds of caching. There's like complex logic to like construct tensors on the fly. And then you want to like memory layout to be good. And then there's like special features, speculative decoding, LoRa's, just like a lot to build yourself. And so if you want to get like full power out of these things and to run them performantly, you're gonna want a framework. So my strong recommendation is the vLLM inference server. Started as a Berkeley academic project, introducing the idea of paged KV caches, sort of virtual memory for transformers. And this is the one that is kind of like won mind share as an inference server. I think I'm hearing more recently also about SGLang, structure generation lang. That one is like also getting some traction, but vLLM is really the one that's like, the Red Hat is contributing to it, and Anyscale is contributing to it. IBM is contributing to it. They've like attracted a like critical mass of external contributions. Like that's a very important piece of like a healthy open source project. And it kind of has an interesting structure, which is like they only run PyTorch models. It's kind of like that's their like narrow waist. But then like anything, the ambition is to do anything PyTorch does, which means also like, you can have all kinds of different accelerators, and you can have all kinds of different frameworks on top of it. So I think that's a good idea. And it's also like the easiest to use of all the options. Like it's a simple pip install. They have this nice OpenAI compatible API layer for integrating with other services. There are some other options. TensorRT and TensorRT LLM, this combo from NVIDIA, is technically open source in that you can read the source code, but it is like not open governance in that there's like one contributor, NVIDIA. If you wish to submit a patch, you like submit it via email to an engineer who then does it for you, not like a PR. And then like also the commits are like 10,000 lines at a time every couple of weeks. So good luck Git bisecting to figure out where a problem came from. So like they do like transparently, like they do beat vLLM on benchmarks, and like vLLM speeds up and then they speed up, and vLLM speeds up and then they speed up. But if you're like trying to build this, you're investing in building this thing, it feels safer to me to build on top of like an open governance, open source project that you can kind of see into and influence. I think, the others, not a ton there. So the summary is like generally very good. Like they care a lot about performance, but they aren't always the like top performer. So the purple bar in all these graphs is like in the middle, not at the top or the bottom. The focus on that was a lot on performance, and like also like when I was talking about the hardware, was like we got to run these things fast, and this is like basically because these are like high performance computing workloads. And once you've like started to pay money for high performance computing on an accelerator, like performance becomes like a very like top level feature. And so when you have workloads like this, you need to do a lot of like performance debugging and not just regular debugging. So there's a bunch of great tools for this. PyTorch has a built-in like memory profiler, and trace trace generator and profiler. Those are all pretty nice for like load testing these things. I kind of like Locust. There's also, I've seen a bunch of people using Vegeta. That seems to be like a hot new load testing tool. Those are both nice if you want to get those in like as early as possible in this process, because it's like this is a performance critical workload. Okay. I haven't been pulled off the stage yet, so I'm just going to keep going. All right, so integration. We've made this thing. This new thing needs to like integrate with the other pieces. Like the part where you're like just doing like, you know, getting APIs to talk to each other is like boring software engineering, like doable. There's not anything that exciting there. The interesting part is integrate like more deeply. How do you like integrate LLM features, integrate things built on LLMs with traditional software? And like, what does that mean for like setting up an LLM inference service? So the key thing here is structured outputs, like ensuring that LLM outputs match a schema. So for example, they pass a regex, they do or do not contain a particular value. They like are possible to be like serialized, deserialized into a typed JSON object. They like fit a Bacchus-Noor grammar. Like these are all actually things that you can add to LLM outputs very straightforwardly. And now they like behave a lot more like traditional software outputs. And so traditional software outputs make good traditional software inputs. And so this is kind of like the layer in between the like floating point chaos of and the like unstructured Unicode sequences that go in and out of LLMs and the pristine software elsewhere. And this, you know, the vLLM actually also includes this outlines library as like built in, just ready to go to add this feature to your like to stuff on the fly. Just like submit with a request, include like some you know, decoding grammar that you want to use. And a lot of the, just a small call out, like a lot of these approaches will like presume the existence of an OpenAI compatible interface, which is built into vLLM, not built into TRTLM or Triton, the like parts of the NVIDIA stack. So like you're gonna have to build that yourself if you don't use vLLM. This is sort of the like benefit of this more like open stack. The models are now actually like trained to be good at this. Like at the beginning, you were just like sort of, it was like very much coming from these grammars, like enforcing this token must come out, not this token. Now the models are like better at following instructions to generate of a particular grammar or generate JSON outputs. The one tricky bit with this is it's very easy to break this behavior. There's a bunch of like configuration files for things like chat templates and tokenization that is like, all that stuff is like, it's just a bunch of like untyped JSON files sitting around in Hugging Face repos. And it's like, and then there's like bespoke logic for loading those things in, and it all fails silently and then just results in the model like putting out garbage sometimes. And so you have to be like very careful with making sure that these things work. But the flip side of that is like, that's because the models have actually been like trained for these things, and the tokenized been set up for these things, all this stuff. Yeah, I think some of this stuff is like fairly detailed, but the high level thing here is, I think, very durable, which is like taking LLMs that take in just like whatever Unicode sequence you want and then spit out a type JSON object is basically like the most extreme version of Postel's law for protocol design possibly imaginable. Postel's law is be liberal in what you accept and conservative in what you send. If somebody sends you a malformed internet protocol packet, you don't like write your congressman about it and like drop it. You're like, oh, you know what? I can actually like, I can work with this. There's like, I can figure out this header. I'll just forward it on and assume that I've made some mistake. Like that's like important part of like making a really durable, extensible protocol. And it's a nice thing with LLMs, like you get that now in this extreme form of like anything comes in and like something that can go into your like database and fit your SQL schemas. It's like, yeah, it's pretty great and feels like a very durable pattern. One like kind of, you could integrate models outputs with traditional software, or you like more deeply integrate and have the LLMs like actually use the software because they can output novel sequences of, they can not output code, they can control things, they could like output those typed JSON schema, and that's like directions for how to use a mouse or interact with the browser. And these are actually really great applications of LLMs. Like if you can find a way to turn the problem that you need to solve into this problem, like an LLM writes code. Actually, a bunch of the initial like best results with LLMs playing Minecraft was actually having them write JavaScript for Minecraft JavaScript bot clients rather than like trying to, summarize the world as like text or like put the image in like, and then have it like decide how to move the mouse. Like it's like just have it write code instead. So if you can find a way to turn your problem into this, you actually might find much better performance. There's like a bunch of reasons for this. Lots of code and computer use info on the internet. Internet's full of people who like computers. Crazy. The people who make models like code and they like computers. So like that's what they tend to test their models on. That's what they tend to think is important. The models and the models resemble the people who create them. And then evaluation, like more seriously, evaluation is way easier. Code quality is something that we have a lot of ways to check automatically. There's a lot more structure. You got to abstract syntax trees, maybe, like you can mess around with these things a lot. And computer environments are way better environments for ML than regular environments. ML involves a lot of like try something a million times, a million slightly different ways, and then like collect an aggregate. In the real world, that is a great, like if you try poking a fork in a million different directions, you're going to stick it in an outlet eventually and die. And you can't roll that back. But a computer environment, in principle, it's like deterministic and you can replay it, run something in a deterministic hypervisor and you can literally replay it. And so that makes them actually like a way better environment to like do synthetic data generation and training and inference time compute scaling and all these things that make LLMs better. And so like we're likely to get kind of like working agentic systems in these constrained computer environments long before we get them and on like things that act in the real world. So this is great. It's a very nice pattern, but you can't express in a JSON schema like this code does not pwn my machine, right? Like the model could easily do something like sudo rmrf no preserve root for fun, one person, the literal example was like somebody turned on, not Nano GPT, what was the one, Baby AGI, and was like, please delete this JSON file. And it was like rm-rf star.json. Every JSON file on the computer was gone. Like, yeah, models make mistakes. And so you want to like containerize it. So like you want, like I was talking about like having like a deterministic hypervisor, something that you can roll back. Like it's like a similar thing here. You want these like tightly controlled and constrained environments for them to act in. And so you want to containerize it. It's a great tool for this called E2B. They're like a purpose built. That's the like core product. We also have a product for that, Modal sandboxes, shameless plug. Somebody from our user community kind of like took it and mashed it up with Anthropic computer use, which is probably like one of the most advanced uses of that product so far. My like brief shill for that is E2B and many containerization solutions use Docker. Docker is at a like 1 CVE a year kind of rate right now. And so like our sandboxes are in a safer environment that has 0% rate so far, I think. That's unfair, but using gvisor, which is a security-oriented container runtime. Great. Well, great. That gives me enough time to go through this slide. Yeah, people will talk a lot about RAG. In the end, like on top of like using code or tool use or whatever, it's just hooking up an LLM to a database. It's not worth a whole slide. Yeah, lastly, like we've set this whole thing up. We want to monitor this thing and like improve this thing over time. Like every person who has thought hard about ML, like Andre Karpathy, Shreya Shankar, Hamid Hussain, Josh Tobin, they all say like, this is the workflow, this is the way to do it. These are people who've worked Tesla, OpenAI, like and this is the workflow. You collect data from production, you use that to drive modeling decisions, and then like you need to annotate it, collect it into evals, like specific failure modes, and like monitor and improve this over time. So like, yeah, this is the thing that you need to set up, like quite apart from like, oh yeah, performance monitoring, blah, blah, blah. Like this is the way that you like deliver continual improvement. If you're setting up an inference service for a broader company, like you need to set up some way for them to do this like easily. So some kind of like logging facility. There are specialized tools for this. You can just use Postgres, but like something is very critical. Okay, so I'm at my time. So I'll just say like Modal serverless infrastructure platform helps you run code in the cloud without all the agonizing pain. It's like if AWS Lambda didn't suck and had GPUs, rebuilt the whole container stack from the ground up to make it better and faster, and can support your evals, your inference, GPUs, CPUs, code sandboxes, web endpoints, user interfaces. If you're interested in it, come talk to me. Okay, thank you.